It's about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause this stream is about to start. Get ready wherever you are, 'cause this stream is about to start. Hi, my name is Leonard Facchinetti, and let's write some code together, shall we? It has been almost a year since the last time I said this. Amazing stuff! I have been doing the meetings of the study group for C++, digital signal processing, and JUICE, but not the live coding things. It has been a while. And I have a special guest to kick things off again. Hi, Abby.
Hi.
So, if you have not been watching the meetings of the C++ Digital Signal Processing and JUICE study group, what is up is that we are working together on this little project here. It is eventually going to be an EWI, an electronic wind instrument, but for the time being, it's a prototype. If you have never heard of an EWI, it's a wind instrument. It controls the computer. It's a MIDI controller. So it doesn't make any sounds on itself, but by itself. But when connected to the computer, it can control any kind of virtual instrument. You came up with the idea for this, actually.
I just thought it was cool.
Yeah, we went to a concert and the person was playing the EWI and making all these weird sounds with like synthesizer sounds, and even playing on lower registers that probably no wind instrument would be able to produce, not even like the bassoon. And you said like, ooh, I would like to learn that. And I was like, ha ha ha, fun stuff. And then you said, no, for real, I would like to learn that. And an EWI is overpriced. There is no good reason for an EWI to be that expensive. Like $400, I think, 400 euros. Yeah. Like, let's DIY this. And then we are paying way more than 400 euros worth of our time. But who cares? We are having fun.
Yeah.
So far, we have a Raspberry Pi Pico connected to a cable that is working as a button. So you touch the cable and it's supposed to send signals. And it's not really working. We set this up again and it's not really working. So I guess the first step is to figure out why it's not working, and then we'll try to see what we can do about debouncing. And if you have not been watching the C++ Digital Signal Processing JUICE study group, we will explain again as we go. Anyway, here is the program as we have it so far. And I remember that I changed something about this when we were doing this study group. So I will change it back to how we left it. This is what was up. Oh, and Ben is here. Hey, Ben, it's great to have you here. You're behind our faces. But here you are. Thanks for suggesting that we did this. It was because of your message that I thought it was time to do it again. Oh, and I see a problem. The logo for the channel is on top of our faces. Let's fix that real quick. How about that? Oh, it will show up here in a second. Much better, much better. Professionals here. So this is what the code looks like. And it's importing a bunch of libraries and doing a bit of setup. But then it does some interesting things. So let's recap. Do you remember what this does?
So let's see. Was it really the way we wrote it? Because I can't. It goes on and off, something like that.
Yeah, this is how we left it when we were last working on it.
Because we don't want the sound. Oh yeah, I remember. At first, when we had the code without, I think the second part, it was just going on forever. It didn't stop, and it was adding on to it. So in the end, we have code to be able to put it on when we touch it, and when we take our finger off, then it turns off. It stops.
Yeah. Remember how it sounded like before we did the fix?
Yeah, it was crazy.
We were sending many note ons, so it was triggering a note over and over and over. And first of all, it would never turn off. But second, it would be super loud because it was always on the attack of the note. So as if you were blowing into the instrument as hard as you could and doing that in a loop as fast as the Raspberry Pi can actually send this note on message. But with the code like this, in the way that it's written now, it is remembering the previous state of the button. So it's remembering whether or not it was pressed on the previous iteration. And it is checking if previously it was off and now it's on. So in other words, it has just been pressed. And it's checking if it was on and now it's off. In other words, it has just been released. And then we send a note on and note off only in the transitions. So we are not just looking at the state, we are also looking at the transitions. And this is just to remember the previous value of the button. Now, the question really is, why is this not sending any messages? So let's save the code and I will stop. And the Raspberry Pi is connected to the computer. That's why we can see the REPL down here, the shell, also known as REPL. And now let's run our program. No error messages. So silence means success, means that something is going well. Over here in Reaper, we are recording MIDI from all inputs, and Reaper can see the EWI.
Does it need to be on all channels as well? On EWI? Doesn't matter.
It's now checking for all MIDI inputs. So if we had multiple devices, like we have a keyboard over there, if that was already, if that was connected as well, it would show up here. But I'm saying, I don't care about the device, all the devices, and I don't care about the channel, all channels. And I am armed for recording, and I will lower the volume because when this works, it's going to be loud. But I am touching the button, or I'm touching the wrong button, but I'm touching the button. Oh, see that? That yellow dot?
It's working?
It is working now.
Great.
Awesome. So I will turn up the volume and...
Because we didn't manage to get it working just before.
Yeah, we didn't manage to get it working right before the stream, but now it's working again. So fine. Excellent. And it was a opportunity for me to recap how to connect all the parts. But now if we touch this...
Yeah.
Well, it turned on, but it didn't turn off.
Oh. Oh, it's, yeah. Okay, so it's on forever again.
Yeah, that's no good. And the reason is that it did not send this note off event.
Okay.
So the note just got stuck. I believe, that if I keep pressing the button over and over...
Yeah, it's doing it again.
Yeah, eventually I'm able to turn it off. And we also heard some flickering. We heard like...
Yes.
The reason for that is bouncing. That's what we discussed last time in the study group. So we are correct in our logic of detecting the transition. The problem is when we press the button, which in this case it's a capacitive button because it makes sense for an instrument to like just gently put your finger on top of a pad and not have to press an actual button. But that means that, and I guess even with physical buttons, this is the case. When you are pressing the button, it's not a matter of like it is off and now it's on. For a brief period, like we are talking maybe a 1 millisecond, microseconds, it's really fast. But for just this tiny window, it goes on and off erratically, very fast.
It's very sensitive, right?
Yeah, and also it is not really... we would like to think that things are very precise in computing, but in fact, electricity goes up and down and fluctuates in a very organic way, in fact. So it is fluctuating above, and like imagine that off is here and on is there. So when you press the button, it doesn't go instantaneously from off to on. It goes like this. It goes like organically like this. And when it is hitting that threshold between off and on, it is fluctuating around the threshold and making the button flicker and turn off and on erratically very fast. So that's the fact that we hear. And the solution for this is debouncing. And there are different ways of going about this. One simple way that was suggested by Seawitz on the last meeting is to do a very simple modification to the code that will make the code look like what it was when the stream started today, which is to take this line and do that, which may seem like a weird modification to the code. At face value, nothing should change because previously this line was running after the if blocks. So if this fired or not, it doesn't matter. If this fired or not, it doesn't matter. What matters is at the end, it's going to run. And now it is only going to run if this block is going to run or if that block is going to run. That seems like a weird change to the code because in effect, this is going to run every time that the button changes value anyway. So what's up with this? Well, first of all, let's see if this makes any difference, and then we can analyze why it would make a difference.
Did you try it last time?
We tried it last time on the stream, yes.
So you know.
Well, yeah, there are no guarantees. No guarantees, Abby. Yeah. So no errors, that's always good news. And I think that this volume is probably okay. So now let's press the button.
Yeah, it's working.
It is working.
That's much more smooth than what we had before.
You try it.
Oh, because I'm touching it all.
The problem with capacitive buttons is that it's very erratic. Even if you just touch the cable, it sometimes triggers.
And then it's not stopping.
And then it's not stopping again. Lovely.
But when you touch just the tip, it works. It's fine.
No, not always.
Not always. Okay. It's better than before.
It's better than before, but it's still not perfect. So now let's try and make sense of why this is even working at all. Oh, and John is here. Hey, what's up? I'm happy to see you all here on this non-study group meeting stream. I'm always afraid that, like, I didn't stream for a while. People are going to forget about me. But it's not like that. People still come. I'm very happy that you're here. So what's happening here is quite interesting. The problem was that we were updating the value too quickly. We were updating this value quickly enough that it was able to bounce from off to on and back to off very fast, because we were checking the value of the button so fast that in that small window, we were able to get that essentially noise in the middle. Now, as far as I understand, the reason why this change to the code works is that we are only changing the value not every time the loop runs, only when we are transitioning. And more importantly, we have this operation here in the middle, the operation that sends the node on and that sends the node off. This takes a little bit of time to run. It takes a little bit of time for the Raspberry Pi to send that message to the computer. It's not a lot of time. It is still probably in the microseconds. It's still very fast, but it is a bit of time. And this is enough time for us to not check the button so quickly, because this line is running, so the Raspberry Pi is waiting. When I'm finished running this line, then, okay, I'm gonna go to the next one. And this time, this interval, is enough for the button to have stabilized on the new setting. In most cases, as we saw, we are still able to make it bounce if we press the button the wrong way. So this is not perfect, but it's an improvement. So another thing that I was thinking about is that we could, instead of relying on the timing of this, which is, we don't know how long this takes. It may not even take the same amount of time every time. It may be running faster once or twice. I don't know. So instead of relying on the timing of this, we could revert the code to how it was. So this, again, runs every time. But if we see a transition, then on purpose, we sleep for a little while so that we are not sampling the button so fast. In essence, we are limiting the amount of times that you can turn on and off in a given interval. Do you think that this makes sense?
I don't really know when it sleeps, if it would make things even more delayed in a way. Because I imagine sleeping would be for a few milliseconds anyway.
Yes.
Yeah. So I guess we could try, give it a comparison.
Yeah. Yeah, well, I guess what I'm going for here is taking control over the timing instead of relying on the implicit timing of this operation. But the principle of why this should work is the same. Okay, so to do a timer, we don't have the import yet. So we import time. And here you can jump in because we have written a timer before. Do you remember how to write a timer? Or to sleep? I don't remember either.
Is it time and then something in between parentheses?
I think it is like this. I forget, but I think it's something like that. And I don't remember what's the unit of measurement. I don't know if it's in seconds or in milliseconds.
Do you have the documentation? Yeah.
That's a good call. Time.sleep, and it seems to be in seconds. And 1 second would be way too much. So let's do like 100 milliseconds.
Yeah. I have no idea how much
I have no idea. No, I mean, this is 100 milliseconds, but I have no idea if this is any good. And because we want to do this here and there, and I will want to be able to experiment with different values here. Do you remember that we went through this? We wanted to have a single place where we would change this number and it would change everywhere.
Yeah.
Do you remember how to do that?
I think it's going to be something like here, like this one.
Go ahead.
Oof, you're asking. It's been weeks. Something like... something like that, right? And then you want it to be 0.1?
Yeah.
Yeah.
And now how do I use this in the in the line 22 and line 25.
Oh well, I should put something else than time sleep, but I guess it would be this. No, I really don't remember. I guess I would put this here.
Go ahead, do it.
But it doesn't make sense to have it twice. Oops.
You nailed it. It's exactly that. The only problem is that this name is already taken.
Exactly.
This name is already the name of this function. So let's just call it anything else. So just rename this into something.
But can I put it? Would you usually do like that? Something like that?
Sounds perfect. And then replace it in the two occurrences as well.
Usually, do you have like a way of writing things so that's... like, do you usually do things like this, underscore?
Yeah,
like
look
that?
at line 16, for instance.
Yeah, right. I'll just make it more streamlined, I guess. Okay.
All right. So can you run this code for us?
Do I need to stop it first?
I think so. When you have the code running in a loop, sometimes the board doesn't like if you just send more code to it.
Okay.
Okay, no error messages. That's good news. And before we test this drum roll, but let's see what people are saying. Bo is here. Hey, Bo. What's up? And even on days when I can't make it to live streams, I frequently watch the recording afterwards. So you should never feel that way. Thanks, Van. You are very nice. I would make a time window of maybe 1 millisecond within the trigger would not run again. Yeah, so I guess that's exactly the idea that we are going for. So we are doing 100 milliseconds instead of 1 millisecond. I think that you are right that a shorter window should be enough. And I often sleep some microseconds, don't we all? All right, here's the board. Test it.
Okay. Well, it's not stopping, but I have to double touch. Okay, it works as an... Oh no, it's worse now. It's doing whatever it wants. I would say it's less precise than before because it turns on and off not very consistently.
That is really weird. It seems to be turning on when I touch it.
And then off when you
off when I release
again.
it.
Yeah.
And off when I touch it again. It's so weird.
But it's not always the case.
But all right, maybe the problem is... Stop it. Maybe the problem is that the window is too large. So John suggested 1 millisecond. Let's try that.
Is that 0.01? I have...
The 0.0...
Okay.
0.01 is 10 milliseconds, and this is 1 millisecond.
Okay. That's a big difference, actually.
Oh, see, that's what happens when you try to save without stopping first. Annoying. Okay, new try. Go ahead.
Oh no, it's doing the same where you have to double.
But now it is bouncing. We hear the drrrr, we hear it rapid firing, right? So that means that 1 millisecond is too little, and 100 is too much. So we can find some happy medium.
Okay. But when it was too much, how do we know it was too much and not just it's not working?
We don't, but I'm going out on a limb here and supposing that that's the case. So let's do in between 1 and 100, let's do 50 milliseconds. All right. Try it.
I'm just...
No!
Sometimes I touch it and it doesn't work. And now I'm touching. No, it's... His first idea, it was Seawitz, right?
Yeah.
Best idea.
Best idea so far. So, okay, this idea is not going so well. And I believe the reason is that while we are sleeping, the person had time to take the finger off the button. So we could continue fine-tuning this, and perhaps we would find a value that works. But what I think is probably the more principled solution, and that does not rely on the timing of this, because we will have more code here. Right now it's simply sending one note, but in the future we will be looking at the state of all the buttons, sending notes, sending velocity depending on how much you're blowing into the instrument.
Yes.
So there are many variables to consider here, and there are many things that will influence timing.
And you want to be able to play fast, like the amount of time you touch is really not that long. Usually it would be about this amount.
If you want to do like thrills and stuff.
Yeah.
So I think that the more principled solution is not to rely on timing. It is to do this, but so we will get rid of the timer. But it was fun to explore this. And I think if we persisted, we would be able to find a value that would sort of work more or less some of the time. But it was an interesting exploration. But my idea is to use a library that comes with the Adafruit thing. And it does debouncing for us. So in this library, we are going to provide the value of the button as soon as we can and as often as we can. And internally, the library is going to debounce for us. So it's not going to let the value change too fast.
Okay. Does that library exist?
That library does exist.
Okay.
And we will learn about it now because I have not worked with it before. So we'll learn about it together. And this will be an opportunity for you to see how, oops, this is my search history. I don't want to show it. For you to see how you come up with this code. Because so far, everything that we have done together was like something that I have already tested before, or a variation on what I have already tested before, but you had not seen how to dive into the documentation and stuff, because that can be a bit daunting. So I wanted to start with like a
pre-made.
Start with something more certain, and then go off, and that's what we are gonna do now. So Adafruit debouncer. And
it's on the 1.0, so
it is the latest, which is what we have. But it is part of
Tix. What is that?
I don't know. Please ensure all dependencies are available on the CircuitPython file system. So what this is talking about is the Raspberry Pi, when you connect it to the computer, it looks like a flash drive.
Yeah.
And this is what comes in it out of like of just installing CircuitPython. But there is this place here for libraries. In fact, we are already using a library to do MIDI. So this stuff, MIDI is what we send, the messages we send to the computer to play notes. That is already a library that we installed. And it comes with many parts, in fact. And there is another one. I think that's how you install this. So let's go here and download this again. Do I download it from here or from the releases? I think I downloaded from the releases. And we are talking about, what version of CircuitPython are we running? 8. So we want this one. And not only I showed my my browser history, now I'm gonna show my downloads folder. So vulnerable. Don't look at it. Don't look at it. I'm in the clear now. So here are all the libraries. There are lots of libraries to do lots of stuff. In fact, when I first looked into this, I thought, I'm just going to copy all of them into the Raspberry Pi. And no, there are so many libraries for so many things that there is not enough space in the Raspberry Pi to load all of them.
You have to make a choice.
So you have to make a choice. And we already have the MIDI.
And we need the Tix.
I think... So, okay, here on the left is the bundle of libraries we have just downloaded. Here on the right is our Raspberry Pi. It shows up as this flash drive called CircuitPy. And here is our code in a Python file. And here is the library folder with the Adafruit MIDI library. And now let's look for Adafruit debounce, which is there. So we copy that. And then we should be able to use the library. So let's go back to the documentation and learn how to use it.
You don't want to... So the dependencies you're talking about, we already have them?
I don't know what this is. The Circuit Python we already have. That's the environment that we are running when we press play, or even the fact that there is this file system here is already Circuit Python. Adafruit Ticks, I have no idea what that is, but it's saying, please ensure all dependencies are available on the Circuit Python file system. This is easily achieved by downloading this, which we did.
Okay.
And it worked for Adafruit MIDI. So let's just cross our fingers and move on. So we have a usage example here, and in this case, it is using digital I/O. It's using a pin, and it's doing a button. This code is doing a button. So it's very similar to our button. The only difference is that our button is a capacitive button, so we are using touch I/O. And they are having they have a literal push down button. Okay. So that's why they're using this digital I/O. Anyway, the important thing is that they are importing this library. So let's
do the same.
Let's do the same. Then they are taking this pin, which I suppose in our case would be our button.
Yes.
And how about we keep this side to side instead of switching windows all the time? I will turn off this side pane, put this window here on the right and the usage example on the left. Much better. So instead of pin, we will do something similar with the button. Like so. And then we have this switch. And then while true, we have the while true here, and we switch.update.
Okay, so all the things like pin direction, pin pull, we don't do because we're having a different type of button.
Yeah. So we sort of have something similar to this, in fact. Remember that we had a problem the first time, and this is not something that we did on, I didn't talk about this on the stream, I don't think. But when we were playing around with this, the first time that we tried to use the capacitive button, it said, oh, you need to install 1 mega ohms resistor to be a pull down, so you connect it between the button and ground. True. So we did that, and if you look at the board, besides the button, there is also a little resistor here. And this is a 1 mega ohm resistor connected between the button, which right now is this cable dangling, and ground. So we already did that. So we did a pull down in our case. It was not a pull up, it was a pull down. But we did it in hardware instead of doing it in software.
Yes. Okay.
Anyways, so now with this update, it is doing the work that we were doing by hand here with the button previous value and stuff. Because now this switch, it can tell if you have just pressed or if you have just released and what the value is. And it is going to be doing the debouncing internally for us. So with the use of this library, we will be able to write code pretty much like what we wanted.
Exciting.
Yeah, so we can get rid of this extra work from here and from there.
Okay.
And all of this becomes that. And all of this becomes that. How about that?
So the part that says print just pressed, we don't do.
Well, this is what happens when you press the button. In this example, they are just printing something here to the console, to the shell, to the REPL, all names for the same thing. But we don't want to print something here. We want to send MIDI notes.
So it was used for something else.
Yeah, this example was using a push down button instead of a capacitive button. This example was printing stuff to the console while we are sending notes. But the important part here was the debouncer.
And what about the switch value, the last one?
This one we don't need. We don't need to tell if it is pressed or not. We are not interested in the state of the button, whether it's pressed or not. We are interested in the transition between not pressed to pressed and vice versa.
Okay. All right.
Does that make sense to you?
Yeah, it does.
Does that make sense to you? Well, cross your fingers. Oh no! No module Adafruit ticks.
No, we don't.
We did not bring in all the dependencies. Let's see if it is here. Adafruit in.
They did warn us.
They did. I thought that they would include it in the debouncer.
There it is.
There it is.
Well, that was a quick fix.
No errors. That's good news. And now go ahead, press the button.
All right. It's kind of not stopping.
It is doing the right thing, but in reverse.
Yeah.
It is doing the right thing, but in reverse. Okay, so
Interesting.
I will mute this for now, so we don't have to keep listening to this note while we work on this, but it seems like we just got this reversed. Is there any way to change this? I don't think so.
What about the order? Because fell and rose, perhaps, if we do the opposite?
Yeah. I'll never learn. And the note is still going, but hey, try now.
Oh. That's good.
That's amazing. That's what we wanted all along.
Yeah.
The magic of just bringing more libraries into the situation.
But this one is more... Yeah, this is much better.
This is perfect.
Yeah, that's what we need.
That's exactly what we need. Internally, this library must be doing something related to timing. It must be doing something like when the button has changed stage, don't read so fast. Like wait out a couple milliseconds or a couple microseconds, I don't know. Maybe it's doing some even more sophisticated things. Who knows? But
then the code is very short. Now the code is actually much smaller than it was.
Yeah, and I would say much more readable. I like how these things read off the page. It makes sense. It doesn't really make a lot of sense. It seems backwards, but I guess it's backwards because here they did a pull up and we are doing a pull down. Our resistor is connecting to ground while their resistor would be connecting to 3.3 volts if they had done this in hardware. And maybe there is some way to invert this so the code makes more sense. Let's take a look real quick. So while this was an example, here is an extensive documentation of everything that the library can do. And there's not a whole lot. Let's see the other pages. Maybe something comes up. The bouncer button. That's not what we are using. We are using this. And current duration. Return the number of seconds since the most recent transition. See, we can even fine-tune this. The thing that we were trying to fine-tune before, we can fine-tune this, but it seems like the default is good enough for us.
Yeah, the bounce delay in seconds. That's great.
Yeah. And
return whether the bounced value went.
Must be called frequently. Cool. Yeah, there is no way for us to say that we want it the other way around.
That's okay though. It's a small thing.
Yeah. Right. Debouncing worked.
Yeah.
Now,
so what's next?
Well, I was thinking that one thing we could do is to have more than a button. Because in the EWI, we will have at least 9. But probably we want some for the thumbs as well.
Yeah, we were talking about those, how do you call them? The one that does like a trill.
Ah, like a mod wheel or a pitch bend.
Yeah.
So we will have...
maybe on the thumb, if possible.
So we will have like 9 buttons or more. And the question that I have is, these capacitive buttons, they seem finicky. With the debouncing, it's better, but they're still finicky. If you put them side to side, then are they going to have any interference? Are you going to press one button and the button on the side is going to think, oh, I'm pressed as well? So I am interested in knowing if we start doing more and more buttons, if they will all work.
Yeah.
So I thought perhaps what we could do is maybe have like 2 buttons to begin with, but
and then
place them side to side and start playing them. And then I guess what we are doing is going to be kind of like a keyboard, because you press a button and it plays a note, you press a different button, it plays a different note, and even you press like 3 buttons and they play 3 different notes simultaneously. So we're kind of building a keyboard on the way of building the EWI. But yeah, I thought that could be a nice next step.
I think it's a good idea before we try a lot of things or put all of the buttons and realize it doesn't work.
Yeah. So to do that, we are going to need first the circuit. Let's work on the circuit and then the code. For the circuit, we will need another one of those resistors, 1 mega ohms, and another one of these little cables. And
which you have here.
I already have the cables here, but I didn't bring the resistor. I will go get it. But we also need to decide where we are going to have our second button. So for that, let's check out the Raspberry Pi Pico pinout. The button that we currently have is on port GP16. Which happens to be this one at the bottom.
Yeah.
So I will go get the resistor, and you can select a number you like.
Is it? Does it matter?
It doesn't really.
Like, can I put it like just next, like a GP18, for example? Or is that not a good idea?
Yeah. So in principle, I would say it doesn't matter, right? In practice, it may. That's the thing. I don't know, because the capacitive buttons are so finicky, and maybe the capacitance of a button is going to influence the capacitance of the button next to it. So maybe we could do like 16, 17, 18, 19, and so forth. Or we would have to skip and do like 16, 18, 21.
Yeah.
So they don't interfere. I don't know. That's exactly what we are interested in testing. So I will go get the resistor real quick.
I wouldn't do the one beside for sure.
Huh?
I wouldn't do GP17 because it's right beside, and we have plenty of space.
Well, how many buttons do you think we will have overall in the end?
Maybe 11, because we're talking about these fingers. Oh, no.
Well, let's see how many GPIOs we have. It goes without skipping, so we have 28. So we could skip. We could skip. We have enough. And here is my box of 480 resistors. So we will have enough for this project. And here are the different resistors with different resistances. And we are looking for 1 mega ohm.
I had no idea there are so many different kinds, actually.
There are many different kinds, and as you can see, they are in my box, they are sorted by resistance from lowest to highest, and R is just resistance, K is 1,000, M is 1,000,000. So this is the highest resistance resistor that I have. And typically projects would not use resistances much higher than this anyway.
Okay.
So here's a resistor. And I'll ask you to place this resistor between your favorite GPIO and ground.
So I was thinking of the GP18 and ground, which is just beside, right?
True.
Oh, but it's already taken. So is there like that spot just beside works? Oh,
well, you can use a different ground if it comes down to that. That's why they put so many.
Yeah, you're right. It makes more sense because it's so close to each other.
Or you can even do the other side for that matter, if that makes it easy.
It does. It's possible, right? From 15. And then... Is it this one? It's so small. I can't see it. Oh, gosh. How do you make it stick? I can't remember how we did last time, so I'm not doing a very good job.
Well, I have big, bare hands, so when I do this, I always use pliers. Do you want me to get some pliers?
Sure. Because they're not sticking in. Okay.
Here are the pliers that I often use for this task. And that's the thing about working on electronics. It is in theory like, oh, you just connect this. And then in practice, you spend like half an hour trying to like, it's not getting in.
It's okay if it touches the board, or does it matter?
It's okay for it to touch the board.
Does this look normal?
It looks okay to me. It looks exactly what we needed, yes.
Then I guess it's
And then let's connect another one of these red wires here. Is it in? It's in. All right. So here we have it. Oh, it's out of focus for you all, but we just have a symmetric arrangement here on the other side. And in theory, you are never supposed to work on the hardware when the board is still on. Yeah. But in practice, the Raspberry Pi is running in 3.3 volts, which is a low voltage, so you will not get shocked. You will not get zapped by the Raspberry Pi.
Thanks for telling me after I did it.
It was the first thing I told you when we started working on the project.
Okay. I forgot already.
There is nothing you can do here that will harm you. The voltages are very low. And the board does have protection against short circuits and stuff. So if you connect something like 3.3 volts directly to ground, that's a short circuit. Usually when you short circuit things, they start to burn or like catch on fire and stuff. But the Raspberry Pi has some protection for that. So it just turns itself off or something. I mean, don't go relying on that too much because you may burn your board and then you have to spend 5 more euros on a new one. But it's nice that you can just play around without fear of consequences. All right. So that is set up. And Fotis is here. Hey, what is up? Oh, and the special guest is Abby. And Not Was One is here. Hello, hello. What about capacitive touch switch? That's what we are doing, in fact. That's what we are doing. We are doing capacitive buttons because it's going to feel like a wind instrument. It's a lot of resistors. Yes, it is. Resistors are probably the cheapest component you can get. A box of 480 resistors with all the values that you typically find in circuits is, I guess, 6 euros. All right. Now let's write the code for this. So the principle is here. We just want more of it. The same way that the principle was on the board, we just wanted a copy. We just want a copy. So I'll let you drive this. Looking at the code, what is something that you think you should copy and paste? Because essentially we're going to be copying and pasting, renaming values.
That one here.
Yeah, that's a good one. So go ahead.
But the part that I'm not sure of is this. Do we name it like button 2 then? Something like that? Yeah, you can do that. Okay. Or is it normal to do like 1 because you have 0 and...
Good thinking. Programmers start counting by 0.
Yeah, and I usually don't.
Well, I guess the Raspberry Pi also didn't, right? Mm-hmm. Will you excuse me? May I look at the pinout again?
Mm-hmm.
Oh, they start counting at 0. Mm-hmm. So we don't have 28, we have 29.
And that's actually what we need to know. 15, right? Mm-hmm.
Yes, yeah. GP 15. Go ahead.
Okay. That's it. Then here, the notes.
Go ahead.
Let me see. I don't see that thing anywhere else. So do we just copy everything again, or do we add this here?
Well,
not sure about that.
Even before that, I will give you a hint. Even before the while true, there's another line that you want to address.
Not sure. Here, this line, I'm not sure I understand it, but...
This line is just setup, okay. So don't worry about that. It's setting up MIDI, in fact. It's not even working with the button at all.
And I don't imagine we would change this, the debouncer either, would we?
Well, we want to debounce the other button, right?
Yes, true. Button is not just a button. It's only the first one. Do we need to copy the whole thing?
Yes.
Yeah?
Uh-huh.
Okay. Then I need to write down switch with I need to rename it, right?
Yeah, you will need to do
like put
_1 on the switch as well.
This is like slow.
You mean to type?
I mean, yeah, if you do that with everything.
You are already feeling the pain.
Yes.
So first we are going to feel the pain of what happens when you have to copy and paste a lot, because we will have 10 buttons. Then when we are on button like 2 or 3, you will be like, I don't want to copy and paste anymore. And then we'll find a clever way of checking all buttons in one go.
Okay.
But first we need to understand the problem and then, and even test the capacitive thing to see if that's going to fly before we try to be clever and generalize the code.
Fair enough.
So switch 1, it's defined. Now let's use it.
So I'll just do this. Did we save and then run? Okay. So
Okay, no errors. That's good.
Wait, we're missing the note.
We are missing the note.
Yeah, of course.
Go ahead.
But that's the part where I'm not sure how you write that.
Okay. So I'll give you a hint. For the time being, we are going to copy and paste the entire block.
Starting with while true?
Well,
no,
then everything inside the while true we want to do twice.
Okay.
Once for each button.
So, to be clear, I've never done Python. Can I do this with a space, like everything? Okay.
Yeah, the space is fine.
Doesn't matter. Okay.
I don't know. I haven't done a lot of Python either.
I don't really recognize C5. I wouldn't know what to change it for.
C5?
I know C, but I don't know the 5.
Okay. I can show you real quick.
Is that the octave?
That is the octave.
Okay.
So here is a piano, and C5 is this middle C, or no, C4 is the middle C on the piano.
So we could do C4, for example.
We could do C4.
Yeah.
That's going to be C in a lower octave.
Okay. And I think that's the only thing we'll change, but How does it know which one to assign to?
How does it know which button is which?
Yeah.
By these variables.
Okay, so then I need to change here. Is it that one? Only that one, or all of? Yeah, all of them.
All of them.
I can see that. Oh gosh. I feel like an elephant.
Nothing makes you look sillier than using someone else's keyboard. It doesn't matter.
No, but I mean having to fill in everywhere. Okay.
All right, try it.
All right. That one works. Yay. What happens? Yeah, you can do both too.
Amazing.
Right.
Do you want to perhaps change it so that they're sitting right next to each other on the board to see if there is any interference?
Yeah, that would be a good
Or maybe
idea.
even just this. I will try and touch the cables to see if they interfere. No, they don't. Even with the cables touching. That's a relief.
That's good. No noise. Okay, but yeah, if you want, we could put them beside each other.
Just out of scientific curiosity, I want to see what happens when it's on GP16 and GP17. Okay, I will do the elephant hands here. This time I will be... hang on, but I want to stop this.
Yeah.
Because I don't want to be playing notes while I do it. Okay, so I will take this resistor out. And I'll put it here.
Suspense.
Yeah.
Why would we do this? It's much more complicated for ourselves.
I'm just curious to see, because I love the idea of capacitive buttons, and I have always thought, oh, I could do this, I could do that, but I wonder if it would work because the capacitive buttons are finicky. So now it does not look so great, but it seems to be in place.
Okay.
Oh, but then I don't have enough.
Right? There's a question of just space.
There. So changing this to 17 and running.
Okay, this is great. It works.
It works. So in theory, we could have 29 buttons if we
I
wanted.
think you should show it.
Yeah.
It really looks like they're on top of each other. Oh, okay, it's normal.
Yeah, I'm pressing the button as I am showing it. Out of focus, I
It's
know.
very
The camera is on
sensitive.
manual focus. But I also have this view. Let's play around. Let's play around. I also have... Oh, hang on. I also have this view, which is the webcam. And the webcam will let me show you this from up close. See? It's pretty crowded in here. And I could take some of these wires and wire things out of the way and then do the rest with the resistors and stuff in a part of the board that is less crowded. But the whole point was to make it very crowded to see if the capacitance would be thrown off. It isn't. It seems to work. So, with that, do you want to do more buttons just in case? But I think we should be okay.
It looks
should
okay.
be okay.
Looks
Should be okay.
positive. I guess the next thing is really doing the bottle.
Oh, you want to do the bottle?
Well,
I was thinking of doing the microphone.
okay, well, that's possible too. Yes.
So I guess there are three things that we can work on. We can do the physical construction, but I think we should leave this for last.
Don't you want to see? So you think this confirms that even if they were beside each other, they wouldn't be?
Oh yeah. Well,
Interfering?
here's something we can do. I will hold this for you very close.
They won't be that close though.
They wouldn't be that close. But now press them.
Yeah, that's
It
good.
works. It works.
Yeah.
We were not like on frame,
They're
but
like
but trust us, it worked.
1 centimeter away or less, maybe half a centimeter. Okay.
So I guess this part is, we can leave it for last because
Yes.
it is gonna work,
Okay.
guaranteed, 100%.
So that's great. And the microphone, what do you want to do with it next?
So the microphone is the other part of the picture, which is the intensity, how much you're blowing into
The
it,
pressure.
the pressure. Do you want to get into that now, or do you want to leave it for the next session? Are you feeling like we are in a groove and you want to keep going?
We could keep it for next session. It's like a whole new chapter.
But it has been a great success today. We debounced, we did multiple buttons. I'm very happy.
Me too.
Yeah.
And it all works perfectly.
So I would say like a fanfare. Like, hang on.
What is that?
Dun, 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 dun. All right, so next time we are going to work on the microphone. We already have the microphone module. It is a little microphone along with an amplifier. And this here, this tiny screw, allows us to control the sensitivity of the microphone. Because if we had this microphone for a project like someone is... you mentioned this the other day, like you can clap and turn on a lamp and clap and turn it off. So we would be clapping on the other side of the room. This microphone would need to be very sensitive. But in our project, we'll be like on top of the microphone. So it needs to be very insensitive. And that's what this screw is. We will adjust it. And then here, we will need two of these pins is to power the board, and the third pin, therefore, one we are going to ignore, but the third pin is going to give us a reading of the intensity of the microphone, or the level of the microphone.
And we don't have to blow that strongly either, right?
Yes, and we will adjust the screw so that we are able to do like versus, and we will see the signal coming from the microphone in the oscilloscope, and then we will plug the microphone module into the Raspberry Pi, and we will read the signal from the microphone. And with that, we are going to inform the velocity. So here the velocity, the intensity of the note is fixed at 120. But it can go from very subtle, like all the way down to 0, up to 127. So there is a lot of nuance, a lot of difference in the intensity of the note. So instead of hard coding 120 every time, we will be looking at the value of the microphone and setting this accordingly.
Okay.
So
exciting.
Yeah, that's what's coming up next. For the time being, I want to say, let's catch up with what you all have been saying. Oh, I can react to my own stream. How nice. I love it. You could write blah blah in all 10 buttons and then search and replace the blah blah with the one you want in all documents using Notepad++. Oh, so this is an idea of how to do the copy and pasting that you were talking about, that you don't want to do in like a streamlined way. Instead of trying to think of a clever code solution, we could just find a cool way of editing the text so that copying and pasting is not so painful. And this actually reminds me of something that I want to point out, which is cool here about Thony, which is this editor that we are using. Previously, you were looking for all occurrences of the button to see where you would need to change. And if you select the text, it's not doing it anymore. But I think I saw it doing that.
Yeah, it was working before.
It was working before.
I don't know.
It was highlighting all occurrences of the button.
And blue, yeah.
Whatever.
So that was helpful, yeah.
Oh yeah, I've been there. Using someone else's keyboard and mouse is like exploring uncharted territory. It doesn't even matter if it is the same keyboard that you're used to. Like if I usually use a Mac. So if I go to another Mac, the keyboard is the same. And still I'm like, uh? And all right, so let's wrap this up. I want to first thank Fotis and the three runmen. Is it how this is how you pronounce your handle? Nod was one, John, Bo, and Ben. Especially Ben for suggesting that I should go back to doing my live coding streams. I want to thank you all for being here on the chat. I also want to thank everyone who is watching this in the future, like Ben says that he sometimes does. And especially I want to thank you, Abby, for coming up with the idea for the project and for helping me out along the way and for streaming with me. It's the first time that I have an in-person guest doing some hardware. That's a lot of fun.
And it was my first time streaming.
You are doing great.
Yeah.
All right. I'll see you on the next one. And I'm not committing to a schedule yet, so I'm not sure when the next one is going to be, but make sure that you smash that subscribe. No, I'm not doing that. Bye, everyone. Thank you for watching the stream. You know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all will be back together for some more coding or talking or chilling. The next time I'll be streaming.